In the previous video, we talked about stochastic gradient descent and how that can be much faster than batch gradient descent. In this video, let's talk about another variation on these ideas called mini-batch gradient descent that can work sometimes even a bit faster than stochastic gradient descent. To summarize the algorithms we've talked about so far, in batch gradient descent, we will use all m examples in each iteration, whereas in stochastic gradient descent, we will use a single example in each iteration. What mini-batch gradient descent does is somewhere in between. Specifically, with this algorithm, we're going to use b examples in each iteration, where b is a parameter called the mini-batch size. So the idea is that this is somewhere in between batch gradient descent and stochastic gradient descent, and it's just like batch gradient descent, except that we're going to use a much smaller batch size. A typical choice for the value of b might be b equals 10, let's say, and a typical range really might be anywhere from b equals 2 up to b equals 100. So that'll be a pretty typical range of values for the mini batch size. And the idea is that rather than using one example at a time or m examples at a time, we're going to use b examples at a time. So let me just write this out informally. We're going to get, let's say, b, for this example, let's say b equals 10. So we're going to get the next 10 examples from our training set. So that may be some set of examples, xi, yi. If it's 10 examples, then the indexing would be up to xi plus 9, comma, yi plus 9. So that's 10 examples altogether. And then we'll perform essentially a gradient descent update using these 10 examples. So that's learning rate times 1/10 times sum over k equals I through I plus 9 of h subscript theta of xk minus yk times xkj. And so in this expression, we're summing the gradient terms over my 10 examples. So there's a number 10, that's my mini batch size, and this I plus 9, again the 9 comes from the choice of the parameter b. And then after this, we will then increase I by 10, so go on to the next 10 examples, and then keep looping like this. So just to write out the entire algorithm in full, in order to simplify the indexing for this, for what I'm going to write out, I'm going to assume we have a mini batch size of 10 and a training set size of 1,000. What we're going to do is have this sort of for loop, for I equals 1, 11, 21, so stepping in steps of 10, because we look at 10 examples at a time. And then we perform this sort of gradient descent update using 10 examples at a time. So this 10 and this I plus 9, those are a consequence of having chosen my mini batch size to be 10. And this outermost for loop, this ends at 991 here, because if I have 1,000 training examples, then I need 100 steps of size 10 in order to get through my entire training set. So this is mini batch gradient descent. Compared to batch gradient descent, this also allows us to make progress much faster. So we have, again, our running example of US Census data with 300 million training examples. Then what we're saying is, after looking at just the first 10 examples, we can start to make progress in improving the parameters data. So we don't need to scan through the entire training set. We just need to look at the first 10 examples, and this will start letting us make progress. And then we can look at the second 10 examples and modify the parameters a little bit again, and so on. So that's why mini batch gradient descent can be faster than batch gradient descent. Namely, you can start making progress in modifying the parameters after looking at just 10 examples, rather than needing to wait till you've scanned through every single training example, or 300 million of them. So how about mini batch gradient descent versus stochastic gradient descent? So why do we want to look at b examples at a time rather than look at just a single example at a time, as in stochastic gradient descent? The answer is in vectorization. In particular, mini batch gradient descent is likely to outperform stochastic gradient descent only if you have a good vectorized implementation. In that case, this sum over 10 examples can be performed in a more vectorized way, which will allow you to partially parallelize your computation over the 10 examples. So in other words, by using appropriate vectorization to compute the derivative terms, you can sometimes partially use the good numerical linear algebra libraries to parallelize your gradient computations over the B examples. Whereas if you were looking at just a single example at a time with stochastic gradient descent, then looking at just one example at a time, there isn't much to parallelize over, or at least there's less to parallelize over. One disadvantage of mini-batch gradient descent is that there's now this extra parameter b, the mini-batch size, which you may have to fiddle with and which may therefore take time. But if you have a good vectorized implementation, this can sometimes run even faster than stochastic gradient descent. So that was mini-batch gradient descent, which is an algorithm that in some sense does something that's somewhere in between what stochastic gradient descent does and what batch gradient descent does. And if you choose a reasonable value of b, I usually use b equals 10, but other values anywhere from say 2 to 100 would be reasonably common. So if you choose a good value of b and if you use a good vectorized implementation, sometimes it can be faster than both stochastic gradient descent and faster than batch gradient descent.